Alright, so going on to Sequence Series Lesson 6. So this is Unit 5, Lesson 6. We're talking about geometric growth and decay. So again, we're kind of going in a pattern here. We did arithmetic sequence, arithmetic growth decay, arithmetic series. We just did we just did geometric sequences. Now we're on growth decay. Tomorrow will be series. So it's kind of on that same pattern with all three, or these two main concepts of arithmetic and geometric growth. Okay, there's many real-life scenarios which exhibit geometric growth. We're going to look at our first example here to kind of get started. So the Globe and Mail published an article in 2010 stating that the University of Victoria is struggling with an out-of-control rabbit population. At the time of writing in January 2010, they estimated 1,500 rabbits on the UVIC grounds. Okay, if the rabbit population increases at a rate of 20% a year, so right there is our growth rate. Okay, complete the table below giving an estimate of the rabbit population in January 2011, 2012, 2013. Okay, well, we know in 2010 that it's going to be 1,500. That's the start. That's what they told us. And from there, it's going to grow 20%. Okay, one thing we have to understand, we have 100%. 100% means 1. That's if nothing changed, it would be 100% every time. So with growth, we'd go up. It'd be 120%, or 1.2 would be our growth rate. Okay, let's just say, we're going to get to it in a second, but just while we're talking about it, if we had decay of 20%, it'd be 100 minus 20%, which would be 80%. It'd be 0.8. So this would be your decay, this would be your growth. Okay, let's go ahead and kind of color code it here a little better. So here is our growth and our decay example of 20%. Okay, it's how far away from 100 it is. Okay, so in this case, what I'm telling you is you're going to go 1,500 times 1.2. That's going to give you this one. Okay, that's going to be 1,800. Then times that by 1.2. 2160. Times that by 1.2. That's 2592. Okay. Okay, show that the sequence representing the rabbit population is geometric. Okay, to show that, we're going to go ahead and just do them as fractions over each other. So we're going to go 1,800, because that's T2 over T1 equals 1,800 over 1,500 equals 1.2. Then we're going to go T3 over T2, which is 2160 over 1,800 equals 1.2. And I'm going to go T4 over T3 equals 2592 over 2160 equals 1.2. Okay, and so you can see it's 1.2 for all of them. So our growth, or our R, is 1.2, as we stated there over on the right as well. Okay, let's keep going here to part C and D. Okay, if term 1 in the geometric sequence is the number of rabbits in 2010, which term of the sequence represents the number of rabbits in 2025? So it's just kind of a trick question here. 2010, if that's term 1, well, that means we're counting the zeros. So we kind of have to add 1. It's not 15, it's actually going to be T16, because you're counting 2010. Okay. It says its population continues to grow at this rate. Figure out January of 2025. So we want to go, our A is 1,500. Our R, we know, is 1.2 for growth. Our N, remember, it's 16. Okay. So remember, we're going to use the general form here. T sub n equals AR to the n minus 1. So we want T of 16 equals 1,500 times 1.2. 16 minus 1 is 15. Okay, and we get 23,110 rabbits. Okay, and so in this example, the growth factor is 1.2. All right, continuing on. We're kind of looking at an example here, number 2. Okay, geometric decay is when they exhibit going down. Okay, so here's an example of decay. So Vinny borrows $10,000 from his parents to buy a car. His parents lend him the money interest-free as long as he makes a payment at the end of each year. They agree on a repayment scheme which results in Vinny owing 10% less at the end of a particular year than at the beginning of that year. This repayment scheme lasts for 8 years. At the end of 8 years, he makes the one final full payment to pay off the loan. Complete the table by determining the amount he owes at the end of each first 4 years. So $10,000 is like his starting amount, like his T sub 0, for example. We want to figure out how much he's going to owe after year 1. Okay, well, after year 1, he's going to pay 10%. Well, 10% of 10,000 is 1,000, so he's going to pay, he still has 9,000 left that he owes. Okay, so he paid 1,000. Okay, so how are we figuring this out? Well, if he's paying 10%, then that means he has 90% of the loan still. So I'm going to be taking the total times 0.9. Okay, that's so we're going to keep doing here. We're going to times this by 0.9. We're going to get 8,100 times by 0.9. I'm going to get 7,290 times 0.9. I'm going to get 6561. The values from the geometric sequence form a geometric to calculate the value of the common ratio. So just to figure out the common ratio really quick, which we already kind of know, so I just showed you, we're going to go 8,100 divided by 9,000. T2 over T1. You get 0.9. So your common ratio is 0.9. And this is an example of decay. So maybe something else we can note. Decay is numbers between 0 and 1. Fractions, decimals. Growth, x has to be bigger than 1. Okay, so geometric growth factor, R, is 0.9. So the growth factor, even though it's a decay, it's just the factor. Okay, determine how much he owes at the end of the 7th year. So determine how much he owes in the 7th year. So let's go ahead and move this up a little bit so we have more room for work. Okay. Okay, so we know that his A is 9,000. His R is 0.9. His N is 7 after the 7th year. So we're going to go T7 equals A, which is 9,000, R, which is 0.9, to the N minus 1, which is 6. So T7 is 4,782. Okay, and so after the 7th year, that means his 8th year, he'll actually pay this amount right here, will be his payoff amount to his parents. Okay, and here's what I just kind of outlined between 0 and 1 is called geometric decay. Okay, so let's look at these options here for decay and growth. So the rate of inflation is increasing by 3.5% per year. Well, we got to remember, 3.5% is 0.035. It's increasing, so it's growth, so I want 1.035 for that growth factor. Temperature of fish in the lake is decreasing by 2%. Well, it's 0.02, but remember, we minus that from 1, so I always go 100% minus 2%, which is 98%, which is a decimal, is 0.98 for the growth factor. Number of rabbits in a population is doubling each year. Doubling is simply 200%. The value of the computer decreased by 1/5 each year. You can think about it as a fraction or a decimal. 1/5 or 0.2 or 20%. Okay, it's decreasing by that, so we want decay. So we need to subtract these from 100%. So let's do the decimals first. 20% take away 0.2 would be 80% or 0.8. Okay, if you want to say the fractions, 1/5 taken away from 5/5, because 5/5 is 100%, you'd get 4/5, which, yeah, 4/5 is 80% or 0.8 as well. The ball rebounds to 3/4 of its previous height after each bounce. It's 3/4. Every time it's going to be times by 3/4. Okay. All right. right, and we're kind of go through next little part here. Kind of proves that there's two different ways you can do it, depending on where your starting point is. All right, so consider the following problem. A rubber ball is dropped from the top of a building 20 meters high. Each time the ball bounces, it bounces back up 80% of its previous height. Calculate the nearest centimeters, the height of the ball after the 15th bounce. Lucasito decided to solve the problem using geometric sequence with T1 being 20. He wants T1 to be 20. Explain why the value of T15 does not give you the problem. Answer the problem. Because if he's doing T1's 20, that's actually at the top of the building. So it hasn't bounced yet. So he's doing before it bounces. So T1 is 20. Actually, T2 is the first bounce. So if that's the case, that's going to move everything back one. So T15 won't be the 16th bounce. It'll be T15 won't be the 15th bounce. It'll be the 14th. So we want T of 16 equals the 15th bounce. Okay, and so by doing that, we can still use his way. So we're going to start with A equals 16. Oops. His A is 20, sorry. A equals 20. R is 0.8 because it's a decay, it's getting lower. N is 16 to make up for that T moving over one. So T16 equals 20 times 0.8 to the 15th. Okay, when you put that in your calculator, it's going to give you 0.70, which is meters, so then 70 centimeters is what he gets for his. Okay, and then we're going to look at Nicolette, who does hers a little different. She argues that T of 15 should be the answer because he found T of 16. So T of 15 should be a solution to the problem. Explain why the first term does not equal 20, because 20 is before a bounce. So she needs to find a T1 then. So she's got to go 20 times 0.8 to get her T1. Okay, 20 times 0.8 is going to get her 16. So her T1 is 16. So A, 16, R, 0.8, N is now she can use the 15. So she can go T of 15 equals 16 times 0.8 to the 15 minus 1 is 14. And she also gets 0.70 meters, which is 70 centimeters. For each student, write an equation where it represents the height of the ball after X bounces. So we have Lucasito and Nicolette. Lucasito's height is 20 times 0.8x, because it was to the 15th. So he's actually using just the x. And Nicolette was 16 times 0.8 to the x minus 1, which hers is more in line with our general form. I probably prefer Nicolette's because I think there's not much confusion. Okay, and moving onward here. Part D. Let's get up to E2 here. Write an equation which could be solved to determine the minimum number of bounces required for the rebound height to be less than 2 centimeters. Okay, so we're trying to figure out when it's going to be less than 2 centimeters. So we want to set either one. I'm going to go ahead and use Lucasito's here. 2s equals 20 times 0.8x. That's the equation. Okay, now we can divide by 20, and we're going to get 1/10 equals 0.8x. Okay, now this is where it gets kind of hard because we can't root x something. So this is where they want you to go ahead and go to your graphing calculator and use the intersect feature. Okay, we've done that before. So in your y1, let's go ahead and put in 1/10. And your y2, put in 0.8x. Okay, and when you do that, you do the intersect, just to give you some time to do that here in a second, you're going to get x equals 10.31. So that means that after the 10th bounce, it's when it's going to get lower than 2 centimeters. So actually the 11th bounce, because you can't go 10, because 10 is still higher. So the 11th bounce will be the first bounce that's under 2 centimeters. Okay, but I'll give you a second here to go ahead and try that. Okay, so hopefully that worked out for you. It's hard to just probably find the window. Okay, now we're going to do the compound interest part. Okay. All right, so Mike invests $5,000 guaranteed investment certificate. Each year, 3% interest is added to the value of the investment at the beginning of that year. Consider the geometric sequence represents the value of the investment at the end of each year. State the growth factor. Okay, so his growth factor, if it's 3% added, his growth factor is 1.03. Don't put 1.3, that's 30%. Okay, it says write the product, which represents the value of the investment after 1 year. Okay, so after 1 year, that should be 5,000 times the 1.03 one time. Okay, and then it says, don't evaluate. So then it says write the one for after 2 years. So that'd be 5,000 times 1.03 times 1.03. Okay, so, or we can also write, you're right, I'm sure you're probably already thinking it, 5,000 times 1.03 squared. Okay, it says use the formula T sub n a to the r minus 1, write an expression which could be used to calculate the value of the investment after 10 years. Simplify, but do not evaluate this expression. Okay, so I'm going to move it up here. Okay, so we're looking at 10. So we know that A is our T sub 1, which we figure out T sub 1 is 5,000 times 1.03. We know our R is 1.03. And we know the general form is T sub n equals A to the R to the n minus 1. So T to the 10 is going to be 5,000 1.03 times 1.03 to the n minus 1. Now understand that since these are timesing, essentially that makes this minus 1 go away. So for the compound interest, and this is because 5,000 isn't our first term really. 5,000 is our second, is our starting amount. It's like T sub 0. Okay, so 5,000, we actually write it 5,000, 1 point, oh, that's sloppy here. 1.03 to the n. Okay, which gives us 5,000, 1.03 to the 10th. Okay, state the value of the investment to the nearest cent after 1 year. So after 1 year, 5,000 times 1.03. We get 5150. 5,000 times 1.03 squared. We get 5304 and 50 cents. And then 5,000 to the 10, we get 6,719 and 58 cents. Okay. So use a formula to write the expression. It could be used to calculate the value of investment after n years. So it just comes back to what we just wrote here above. It's essentially going to be T sub n is going to be, for this example, is 5,000 times 1.03 to the year number. So whatever year number, that's what it's talking about. All right, and the last piece here, part G, it's going to help you just kind of sort it all out. Okay, so we understand from our formula that we know that we need an R, and R is always going to be 1 plus I over 100 for compound interest, because you can't have negative interest, so 1 I over 100 just gives you like 1 point. This case, the last one we just did, we'd have 1 plus 3 over 100, which is 1.03. Okay, and then we know that A equals principal times R, which is 1 plus I over 100. And then we go to our formula, and we kind of plug this stuff in. It'll give us a kind of a compound interest formula that's commonly used. So it's going to be equal to principal times 1 plus I over 100, 1 plus I over 100 to the n minus 1. The same thing with two of these here. We'll cancel that out. So simply, our annual interest is going to be represented by the function p times 1 plus I over 100 to the n. Okay, and that's your compound interest equation right there. And that's it.